I always appreciate Wesley's contribution to the colloquium, and again he's giving a talk this last talk of this semester in the colloquium, and the early January or the mid January I will also make an announcement by email for the upcoming colloquiums in spring. Okay, yeah. So then I'm glad to have Wesley today, and then he'll be talking about the mathematical logics and the probability. Please welcome.
So in the mid-19th century, a couple of mathematicians who would be well respected today wrote some books whose titles would probably not be well respected today. So 1847 you have Augustus de Morgan writing a book on formal logic, necessary and probable. A book about logic and probability. You also have Boole writing Laws of Thought, which is, after all, what logic and probability both are, right? This is not really a modern view of either field, and yet there is some exciting stuff going on where those two fields as they exist now meet. So one area that I want to mention is random sequences.
Random?
Well, that may be random, but I think we would all have an intuition that this is not random. Why?
Intentionally.
What?
Intentionally you wrote that.
Right, but why is it new? Why is this thing that I wrote not random?
All at once.
Yeah, it's all ones. It's all the same. I can really easily predict from nothing what the next element's going to be. Okay, so I should fix this. I should make something where there's an even mix, where you can't make any money at all by betting on what the next one's going to be. Right? If I tell you I'm somewhere in the middle of this sequence, quick, tell me what's the next digit.
1 or 0?
But which one?
I toss a coin.
What's the middle?
What?
What's the middle?
You know, I'm somewhere along in it. I'm at stage N. What's the next number?
And even or odd?
Oh, don't bother me with me. Just tell me what the next number is.
Average one half.
And mod 2.
Yeah, so you can do it by looking at N. You can also do it by looking back at what was the last number. Probability of each one's 1/2, but probability given the value of the last one, that concentrates. So if you fix a particular length of a look-back window, so this one wouldn't pass the test for anything. This one, yeah, it's half and half, but if you get a look-back window of 1, you can predict what the next one's going to be. there are other sequences, and you can build them with a little thought, and Karl Popper did, that if you look at just the previous bit, you can't predict the next one, but if you look at the previous 2 bits, you can predict the next one. Now, this is a much weirder sentence than it looks like. By a computable sequence, I mean that there is an algorithm that given in will tell you the nth bit in the sequence. So, it is really random, and yet, if you tell me in, I can tell you the value of sigma of n.
Computable means you have some algorithm?
Yes, computable means exactly that I have an algorithm that will compute the nth bit.
Okay.
And that really doesn't seem like the sort of thing that should happen with anything random, right? You shouldn't be able to predict it by an algorithm. So this is not a notion of randomness that people talk a lot about today. In fact, I can get a pretty decent fight going among some people even calling it a notion of randomness. But it does actually tie in a little bit with some other things that people have done. Burrell, for instance, worked on things very similar to this. You can view a binary sequence as a real number in the unit interval. Read it as a binary expansion. So you can talk about a random real number, or at least a normal real number. And what Burrell showed is that there are lots of things that are normal to one base but not to another base. So you can take something that looks very, very random as a binary expansion, but maybe its ternary expansion is very regular. Or maybe its decimal expansion is very regular. I mean, I know the idea of thinking about a real number in its decimal expansion is sort of exotic, but these possibilities must be considered. I forgot to put a date on this. It's relevant in light of what I'm about to tell you. So, to find a sequence that has this kind of algorithm to predict the next digit, and yet the sequence itself is proper random, that's a fairly old insight, and I mean, a philosopher proved it. How hard could it be? To prove that you can do this in a way that doesn't go away when you change basis, that is a good deal harder, and a good deal more recent. Now, because this is the only theorem that uses this term automatic, I'll tell you what it means rather than writing a detailed definition. So, there's a few ways to model computation. If you want to model having an algorithm somewhere, sometime, that will run in finite time and use some finite amount of memory, computable is what you're thinking of. If, however, you want to put a bound on the amount of memory it uses, then in some ways you're talking about a very different notion of computation. That's a finite state automaton. And while you can get away with this, with unbounded memory, you do need the unbounded memory. Now, for stronger notions of randomness, it's a pretty straightforward result that there are no computable numbers that are that random. But with an appropriate oracle with access to appropriate other information, you could get one. So there will be an open question to follow this theorem once some more definitions are in place. So, on a first reading, it's a bunch of open sets of decreasing measure. Now, by saying they're uniformly open, uniformly sigma 0, 1, I mean to say that, number one, you do have some algorithm that will tell you in some form what the next set is. And you could think of being uniformly sigma 0, 1 as there being an algorithm that will tell you how it can be composed as a union of basic open sets. the real point here is that I want to say that x is random if and only if x has no special properties. So what's a special property? Well, a special property must be a measure zero set. So x is random if and only if x is not in any set of measure zero. There should be some objections. Every singleton is a measure zero set. So that definition isn't going to quite work. Yes, I have a very special property. I am myself.
That is special.
Thanks. So what we're building here is a way to work around this. What we're trying to build is a definition that says x is random if and only if it has no special properties that are easy to express. So a measure zero property that would be easy to express is one where you can get this nice descending sequence of open sets zeroing in on it. So take any one of these systems of decreasing sets, take their intersection. If x is not in any of those, then it has no easy to express special properties, so it's random. Almost all real numbers are Martin-Left random. No algebraic number is Martin-Left random. Pi is not random. E is not random. Take an integral of an algebraic function on an algebraic domain. You can pick up lots and lots of numbers that way. It's called a period if you've encountered those. None of those are Martin-Left random. If you have a computable expansion in any base, you are not Martin-Left random. And so, almost all reals are this way. It is some challenge to name one. There are a few examples, but they are not at all canonical. and it's really hard to give a concrete example of a random real number. Now there is sort of a standard index for a relatively easy set to understand that's not computable. Computers are getting better all the time, but I think it is still possible to talk about the Microsoft Windows problem. Your computer jams up a little bit, and it just sits there unresponsive. And you wait for a little while, because, maybe it's just slow choking on something, maybe it'll resolve itself. Maybe it's just running the campus anti-malware thing. Maybe it'll resolve itself in a few minutes. And so you wait a little while longer. And it's still not doing anything. And maybe it's a good time to go get a drink. You go fill up your water mug, you come back, it's still, but you don't know when to stop waiting on it. Properly coded up, this is called the halting problem. And if you have read-only access to the halting problem, if you can decide questions like that, then you can compute a Martin-Leff random real. Some of them, not all of them, but you can compute some of them. In finite state automata, there is not really a great notion of a halting problem, not really a great canonical undecidable set. And there's not really a notion of relative computability, at least not a well-explored one. But it seems like there might be some space to make a theorem like that with the right set of definitions over here.
Maybe the definition of ML test actually you do not include the measure is zero.
Sorry?
The measure u over un is actually not zero, right? Or zero is included, or how do you?
Let's see.
Because to make a random.
So I think if one of your UNs happens to have measure 0,
Yes.
I think that's going to be a relatively easy case. Yeah, that is a test that has to be passed,
Okay.
but you have to pass harder tests than that.
All right.
That's the easy kind of test to pass,
Mm.
because you can actually say how to make up this set U.
Not in there, and then there is ML. Okay. Oh, I see. Okay, I get.
Yeah, so you-
They should include the zero. Okay. Yeah. Now. Yes.
Yeah, so maybe these eventually get down to 0, maybe they don't. I don't know.
Yeah. Yeah. Is there a relation between the proper random and the ML random?
Good question.
Yeah.
The theorem that should go here will be my first real piece of evidence that there is a connection.
Oh, I see. Usually, just one is not. It is not easy to say one implies the other.
Oh, yeah, so that we do have.
All
A
right.
Martin-Leff random is very, very, very normal. It's normal and then some.
Okay.
Because you could write down the failure of independence. You could write that down as a test. You could write it down as a test, but what you really could write it down easily as is the next thing, which is equivalent. So there is a broader definition of a martingale that people use, and I am still trying to figure out the exact sense in which this matches that other definition, but I am told that it does if you squint just right and add the right conditions. But the idea of this thing is that it's a strategy for betting on the next bit. And the amount you have now should be the average of what you would have in the next two cases. So by 2 to the less than omega, I mean finite binary strings.
I'm not sure I can read what the other one. You mean non-negative reals? Is that what the other one is?
Yeah, non-negative reals.
Okay. I wasn't sure wasn't a letter or what. I mean, it's all kind of hard to read.
Oh, yeah.
Okay.
Non-negative reals. And if in the long run you can win with this betting strategy, then we say that D succeeds. The importance of this theorem is that having no easy to express simple properties, special properties, having no easy to express special properties is equivalent to an understandable betting function cannot make money betting on your next digit. So with that formulation, the failure of independence here really could be made up easily into a martingale that would win on something that failed to be normal. Pivot a bit and talk about another aspect of this theme of connection between logic and probability. And I believe we are safe in here from anybody who plans to participate as a student in math field day, is that correct? Because I'm about to reveal an answer to a problem. So I take all the graphs that have n vertices and m edges, and I put uniform measure on it, not uniform measure on the isomorphism classes, uniform measure on the graphs themselves. So in particular, this and this count as two different graphs. And each of them has equal probability, but each of them stands for itself. Another way, and it's not at all obvious that you get the same thing here, although up to reasonable approximation you do. Instead of prescribing the number of edges, prescribe the probability that each pair is going to be adjacent. And you get a probability space out of that. You get a probability measure on all of the graphs on n vertices. So the reasonable conditions here are formulate what the probability would have to be to give an expected value of the right number of edges, and a few more things. So, pick a graph at random. What does it look like? We've got two, at least for the almost sure things, they're equivalent. Two different notions of a random graph. Pick a graph at random. What does it look like? Okay, good, it's really a problem. I'll show you what it looks like. And there is absolutely nothing special about 1/2 here. It helps that it's a constant, but even that can be relaxed some. Now, that by itself doesn't exactly tell you what a random graph looks like. But the proof does tell you what a random graph looks like. So, if you get formal about the syntax of these sentences, it takes a lot of them. But you say, for any set of vertices here, I guess I should say finite sets. For any two finite sets of vertices, you can find something that's adjacent to each one of these and is not adjacent to any one of those. And there is a unique countable graph satisfying all of these things, because if you take any two graphs that satisfy these conditions, and you have some partial function that's wanting to be extended to an isomorphism, you can always extend it to one more point. Take the new vertex you want to add, look at all the stuff it's adjacent to, look at all the stuff it's not adjacent to, find something over here that's adjacent to the right things and not adjacent to the right things. You can do the same going the other direction. This condition means that we've completely determined the graph by this. We've completely determined what sentences are true, and in particular what configurations exist in the graph from these axioms. What that also means is that absolutely any picture you could want to draw in your graph exists somewhere in a random graph, almost surely. Because you draw it one point at a time. Okay, I have a vertex here. I have another vertex. Should it be adjacent or not? I have another vertex. Should it be adjacent to this one or not? Should it be adjacent to this one or not? Draw whatever figure you want that way. So the question to what does a random graph look like? The answer to that is, well, everything. It looks like everything, all dumped in together.
Can you give us a numerical example, just drawing how that's behaved?
Well, so for this theorem to be true, you actually have to be looking at almost all, which means you're looking at the limit as n goes to infinity. So in that sense, no, I can't give a numerical example because the examples don't arise until you get infinite. So yeah, these random structures, unless saying, okay, I've proved that there is a unique countable model, there's your example. Anything short of that is not quite an example of a random graph, because if I draw any finite graph at all, there's some probability, some positive probability that it was a different one from that one. Now as they get bigger and bigger, the probability concentrates on one isomorphism type. But you really do have to take the limit to get that concentration.
So you're taking the limit on the probability of
Limit in n. So take all of these sets. So I guess I'm using shorthand here.
okay.
Take all of the graphs on n vertices with edge probability 1/2 and keep accumulating them as n goes to 0. You can see, for instance, that with probability 1 you're going to have infinitely many vertices, because most of the graphs are bigger than that. Pick any number of vertices, most of the graphs are bigger than that.
What do you mean bigger than that?
Have more vertices.
Okay.
Pick any number of vertices, most of the graphs in this union are going to have more vertices than that.
Okay.
Similarly, most of these are going to have a triangle somewhere, because if you flip 3 coins often enough, eventually you're going to get a run of 3 heads. So almost surely there's a triangle in the graph.
So you're looking at G of n 1/2 as somehow as a subset of G n plus 1 and 1/2?
Yeah.
So you're not requiring them all be, they can have more edges than, or more vertices, right? So that's for different graphs, I think.
Yeah, so, okay. So what exactly do I mean here?
Yeah, that's
What I mean here exactly is that the sentences of this theory will be true for a fraction of graphs that tends toward 1 as n tends toward infinity. So there exists a triangle. In a 2-vertex graph, that's probability 0. In a 3-vertex graph, that's probability, I don't know, 1/8 maybe. In a 4-vertex graph, that's probability I don't know what. Keep going. But the probability in the limit is going to go to 1. The probability, as you look at n-vertex graphs, the probability of finding a triangle will tend toward 1. Because eventually you're flipping 3 coins an awful lot of times.
I mean, finding a subgraph that.
Yeah.
Yes.
This is perfect.
By there exists a triangle, I mean there exists x1, x2, and x3 such that x1 is adjacent to x2 and x3 is adjacent to x2. I think
So
that's
that
enough.
doesn't disturb me too much because.
Right.
Yeah. Random sequences are gonna have just about any sequence,
Exactly.
finite sequence.
Exactly. So take any set, take any collection of its subsets. I'm about to define a fairly general construct here. Yes, I know what time it's getting to be. So take all of the different ways you can cut X with elements from C. Count them. Yeah. So, if you have seen something like this before, for instance, in the world of Vahotnik-Chevernenkis dimension, if you have seen the world of machine learning and statistical inference around there, yes, this is exactly the same thing. But right now, it's just a combinatorial principle on what things can be defined in this structure. And the theory of random graphs has this property. The theory we built here has such weird combinatorics as that. When I ask people, what kind of learning theory could we do in a more permissive environment than finite VC dimension? Always the answer a logician gives me is, I don't know, what could you possibly hope to learn about a random graph? And that is a fair challenge, one that I haven't answered yet. Finishing. Okay, I will tell you what this thing does, but first I'll tell you what I've written. So, we're going to take some collection of sets. Those are the possible targets. Think linear half spaces or something. I'm thinking of an element of C. You tell me how many labeled examples you want, and then you tell me what C is. And I'm not going to demand that you be completely right. I'm thinking of a linear half space. tell me how many points you want in the real plane. I will give you that many points and I'll tell you whether each one is in or out. I'm not going to insist that you guess exactly right, but I want you to guess so well that with high probability, in the examples I gave you, with high probability, you aren't wrong by very much. What did I call the distribution? I didn't. So like I say, I'll tell you how precise you need to be. You tell me how many examples you want. I'll give you those labeled examples, and you tell me a linear half-space. And with high probability, your linear half-space should be really close to the correct one. This is actually possible for linear half-spaces. Take the tightest fit to the examples you're given, and because I'm choosing examples according to the same probability you're going to be tested on, if there really was high probability of getting in that symmetric difference, you would have seen an example from there. And when I say reasonable, pick a dozen sets that you would naturally concoct out of this definition and insist that they all be measurable. Who here likes dealing with non-measurable sets? Who here views non-measurable sets as the sort of thing that you would expect to run into in a dark alley? You don't see a lot of them running around, especially when you're doing algorithmic things. Now when you're watching where the rounding errors go, that can be a different matter. But these are things that really should be measurable. So it really is, you have to drill down usually to the original paper to find even the definition of what reasonable cases means. Everybody else just cites this, usually without for reasonable cases. It's written by computer scientists. Usually they leave off that first clause. Non-learnable is equivalent to having the independence property.
There should be something that the machine cannot learn, maybe somehow.
Yes, there is.
I see.
A random graph, for instance.
Yes, there is IP, and IP is equivalent to the non.
Yeah.
All right.
There are lots of more accessible things that it also cannot learn. but that combinatorial dividing line is an algebraically significant one and is equivalent to a lot of really nice things that we like to look at on separably closed fields, pseudo-finite fields, things like that. So there is a large theory around this independence property, and so it becomes an important dividing line.
Is that might be very philosophically, maybe just I don't know much about the machine to those and that, but machine only allowed under some algorithm. So algorithm means the integer, the countable name, right? And the integer
Yeah.
left 0. And then but looking at the behavior of human compared to the machine, and then we do not restrict in the such countable. We do think maybe uncountable or RF1, RF2 or something like that. So is that somehow, do you feel something?
Well, biologically, intuitively I want that to make sense. Biologically it makes only a limited amount of sense because of how synapses work. We think most human thinking is done in the nerves. Yes, there is considerable stuff that goes on that we like to think of as thinking that goes on in the endocrine system too. But if you're talking about what goes on in nerves, things are either activated or not. And there is a transition state in between, but it really does seem to function as a transition state. So a lot of neural computation appears to be highly digital. If it were not, then your idea would have to think of humans as analog computers, which is fine as far as it goes. But Hamming and to a lesser extent Shannon in the early 50s figured out that if you can do error correcting codes on digital computation, it's practically going to do anything you would want an analog computer to do anyway, and generally faster and more reliable. The subject is not exhausted, but I'm aware that people probably are. Are there other questions?
Okay. Any other questions? Okay. Let's thank Wesley again. We have refreshments on the third floor as before.